Okay, so for the session, for record, all students are here. All right. We have completed chapter 2. We have completed finite control element analysis already. We go for chapter 3, flow through pipes. We will look at what happened inside a pipe. So we see whether we can complete all these major points by 6:30. So we're going to look at laminar turbulent flow. Then what is fully developed, and then what is the transition. And then we're going to focus on major loss. We're to calculate loss inside the pipe. And then we'll look at a Moody chart. Look at two equations here. DW, or Darcy-Weisbach equation, and then one more is JC equation. Somebody text me. Oh, finish 6, okay. Right. All right. Now this chapter will be in your test 1. This chapter will be in your test 1. So, okay. Now on your question 1 in chapter 3 tutorial, so you will see all these components when we talk about pipe system, right? So it asks you to complete the name of the basic component. So there's some blank that you need to fill in there. So for pipe system, you have, in general, you have inlet and outlet. Whatever is in, suck in, and then inside the system, and then come out, outlet. So bottom there, you need to fill in, this one is your inlet, which is your, normally we'll denote this one as 1, station 1. Outlet normally is your station 2. Okay, inlet, outlet. And then we have an elbow here. We have an elbow here, elbow, with this change of direction of your flow. Elbow is a mechanism that you use to change the direction, the vector direction of your flow. And then we have a few mechanical property, mechanical component, pump, valve. Pump is to pump something from one place to another place. And then we have a T junction here, or T pipe here, T junction. And then we have valve, VALV. Valve, the function is to release pressure, or to release the fluid, or to channel your fluid to another container or another dimension. And then we have a pipe here, of course. Right. So this consists of typical pipe system, right? So if you go to interview or you go to work later on, you deal with the industry question. Sometimes you need to know, this one is fundamental names for pipe system. Okay, inlet, outlet, elbow, pump, valve, pipe, and the junction T here, right? Junction T here. So these are the name that you'll see in the statement, especially when you want to solve your analytical problems. All this name will see in all these things. Right. So number 2, we have two kind of system. We have two kind of flow system. One is on the left hand side. That one we call it pipe flow. Right hand side is for the open channel flow. So these are the two different systems. So most of the equation in this chapter will be in this category, pipe flow. And there will be one equation later on will derive from open channel flow. Then we apply inside pipe flow. As you can see from the diagram here, the main differences here is the water inside the channel. Okay, so these are all the characteristics. So one is completely filled with the flow, with the liquid, This one is partially filled or do not complete fill with the liquid here, right? So these are the two main characteristic or two main things that differentiate both of them. Okay, and then the mechanism also. Mechanism for pipe system is due to the change of pressure, right? Because of the pressure from one point to another point, and then the flow will flow. So if you look at the diagram here, there's some hidden message here. If you look at the pressure gauge here, so this one point to a certain direction and one point to the one direction. So in this case, it's very obvious to see that point number one have higher pressure than point number two because of the direction of the needle that you see on the gauge here. Okay, normally gauge will go clockwise. So as you can see, the angle of the gauge that you see on the screen here, I point to you now, right? The gauge angle here is different. So one is more pressure than two. So the flow can flow from point one to point two. So it'll give you the direction of your Q. So this chapter, by looking at the pressure gauge or the value of the pressure, you will know the direction of your Q. So this is a hidden message when you want to solve question for chapter 3. Okay, always look for pressure magnitude and then automatic, it will tell you the direction of Q, because why? Q in and out will tell you positive or negative later on. And for the open channel flow, it due to gravity. So here for open channel flow, because it do not fill completely, the only mechanism that drive the flow to flow from 1 to 2 is due to the elevation of the channel. So in this case, the water flow from 1 to 2 is because of the change of elevation. So point 1 is higher than point number 2. Gravity drive the liquid from one point to another point. And then for open channel, pressure at point 1 equal to pressure point number 2. So these are the differences between pipe flow and open channel flow. Okay. So if you're doing final year projects and you deal with pipe system, you have to clearly state or clearly demonstrate your understanding between pipe flow and open channel flow. Right. So usually, if I see your final year projects deal with a pipe or channel, then I will throw some question from this chapter. Right. Why? Because your final year project actually is a summary of what you learned from year 1 until your final year. Right? Yeah. Okay, clear number 2. Question 2. Now we're going to look at what is laminar flow and turbulent flow. Okay. Now, if you do an experiment, later I open one YouTube video for you to view. So this experiment is that we have a flow from left to right, and then we will to monitor the flow of the fluid, we will inject some watercolor or dye so that we can see the behavior of the flow. Right. So for example, on this diagram here, you will see that the flow is in very thin line. So this is called laminar flow. So turbulence means it will go like mix up, and then the color of the fluid will become totally blue. All right. So yeah, maybe you go for this one. You go for take too long. Okay. So let me reopen the slides. Okay, the video one, I'll just skip. Go and see how the experiment do. Right, basically it's just to see the behavior of the die. Right. Then I will summarize in this diagram. So as you can see in diagram number 3, you will see the similar behavior in the video. So for the first one, if you see that the die was stirred up along the channel or along the pipe or inside the pipe, you have a turbulent flow inside the pipe system. So the first scenario is called turbulent flow, when there's a mixture or there's a disturbance inside the pipe, right? And then the last one is laminar, means you have a straight line, means the flow will flow in the uniform and one direction. Then you'll see the die will go in just one straight line, like I showed you just now, the picture that you see on the slides. And the transition from this laminar to turbulent is called transitional flow. Transitional flow is the combination of, it's not combination, but it's the stage where your laminar transit to become turbulent flow. So you will see some deviation or waveform of your die, or you'll see the change of velocity direction a little bit, and then it come back. And then when you become more and more mixture, then become turbulent. So we have 3 types of flow for this chapter 3. We'll deal with this 3 types of flow in this module also. All right. So we look at laminar, turbulent, and transitional or transition flow. This is by experiment, but we are, as an engineer, we need some numbers to quantify the behavior so that we can calculate, or we can prove it in a mathematical way. So this, I think, so far is quite direct. Question number 4, the diagram is at the back, so I think it's the format, the format system. The format when you do conversion into PDF, then right. Question number 4 is referring to the diagram at the next page. Yes. Any
so
question?
out of it's like by the in hydroelectric stations, as generating hydro power generation.
Yeah.
Like which kind, like water turns the turbines, right?
So, you are referring to this diagram, right? That what I saw in the show you on the screen. Yeah. Okay. Yeah.
So is it like a flow to turn the turbines, or it's like position flow?
Yeah. So yeah. So it will depends on what you observe from the experiment. So if you see that the experiment, the flow is in the straight line, like this one, if you see a straight line like this one, then it's a laminar flow inside the pipe. But if you see a total blue color, or there's a mixture of color, then it becomes turbulent. And the transitional process actually happen very fast. You can only, yeah. Yeah, what are you trying to say? Yeah, just now you're trying to say something, so go ahead. Yeah, just now you mentioned about the application of the devices like the water dam and all this. Yes, we'll see turbulent most of the time. We'll see most of the time it's turbulent, and in your house pipe water, it depends on the hose that you use. Sometimes if you use it depends on the setting of your hose. So most of the pipe that you use outside outside your garden or for gardening, most of the time you'll get laminar flow. And then for the shower, normally is you'll get turbulent flow. So from here to here actually happen very fast. So in a later slide, I will show you on mathematics model that how we define mathematics based on the speed that we have. All right. Okay. So this is just an explanation on the velocity component on time. So when you have a laminar flow, your velocity along the x-axis, velocity u, small u is a vector along x-axis. It will be the same value all the time. Then you get laminar flow. Then if you have different magnitude of velocity, different magnitude, this is about magnitude. Sometimes very fast, sometimes it's very slow in a certain point, then it becomes turbulent. Okay, so this is just an illustration. We look into okay. So I think I jumped some slide already. Okay, for question number 4, we'll come back later. I think the slide jumped a bit. So this equation is for question number 5. So to judge whether the flow is turbulent, laminar, or transitional, then we'll use this equation. So this equation is very, very important in chapter 3. So I emphasize again, this equation is very, very important for this chapter. So it's called Reynolds number. Reynolds number equal to rho v d divided by mu. Rho density, v velocity. D is the diameter of the pipe, and the mu is the viscosity, dynamic viscosity. Okay. If your value, you calculate your value of your Reynolds number, this is called Reynolds number. So if your Reynolds number is less than 2100, it becomes laminar. Okay, so if your flow have Reynolds number less than 2100, it is a laminar flow. If the value more than 4000, it is defined as turbulent flow. Value between 2001 and 4000 is a transitional. Okay. So two magic number you need to remember for today. Reynolds number 2100 and Reynolds number 4000. What happened in between is transitional. Okay, this number is very important again for this chapter. Because you solve a question in this chapter, you always start with this number to justify whether it's a laminar question or it's a turbulent question. In this chapter, I can say we do not ask you what happened in the transitional, unless we want to test your intelligence. We purposely give you a value or parameter to come out is fall within 2000 and 4000, and then ask you what is type of flow inside the pipe by giving given the certain circumstances, right? Given the certain parameter. So what is type of flow that you see from the parameter? Means you judge based on Reynolds number what type of flow you have. Okay, yeah. So remember 2100 and 4000, this number. If you get anything below 2100 is laminar flow, then you use laminar flow equation, very direct. If you get anything more than 4000, you straight away use the turbulent equation. And if the number fall within transitional value, you just need to state the stage of the flow. The flow is transitional, and solution is very complex. That is the answer for transitional statement. Okay, you don't need to further analysis anymore. We just say that the condition is transitional, and the flow behavior is complex to analyze. Right, cover Reynolds number. This is called, this for question 5. Question 5. All right, we're back to question 4. So there are some space to fill in. So let's say, for example, you release water from a water tank through a series of pipe and turn. So you have section 1, section 2, section 3, section 4, section 5, section 6. All right. So when you open up the valve into the pipe, the first region, you will have entrance region flow. You have entrance region flow. And then it followed by fully developed flow. Now, if you see from the diagram that you have there, what does it mean from the velocity profile that you see here? It means at the entrance region, you have a uniform flow because the velocity vector is all the same magnitude here. So you have a uniform flow at the entrance, section 1. And then when you reach section 2, you get a profile, velocity profile, parabolic profile here. We call it fully developed flow. This is called fully developed flow, where we can see there's a parabolic profile in the velocity vector there. All right. So you can see that as you move from section 1 to section 2, your uniform flow is decreasing, the zone is decreasing, right? And because of the friction of the wall, the flow start to slow down at the wall. The velocity equal to 0 here, and then it start to pick up the flow, or the flow start to slow down as it's near to the wall. So the longer it go, when you reach section 2, it will become a fully developed flow. Later, we will look at equation in this section. And then when there's a turn, when there's a corner, there's a turn, there's a T or something, right? In this case, I give you an example of a U-turn. Then you have a developing flow. Fully developed flow will change into developing flow, and then it will become fully developed again. So in a pipe system, the flow, the liquid will try to become stable and reach a fully developed flow, no matter it go, right? So in a question, you always have an entrance region, and then entrance region, then you will pass through a stable stage. We call it fully developed flow. And then when it come to a channel, a turn, or change of diversion flow, then we have a developing flow. Means it will start to develop, start to change shape because of the rotation or because of the change of the angle. The phase is called developing flow, and then at the end, you still reach a fully developed flow. Okay, so this is quite direct. It's only a definition of a certain words that we use for chapter 3. Entrance region, fully developed, developing, and fully developed again. Okay. Okay, some notes for this diagram. And we're going to define, if we have for entrance region, you're going to use dimensionless. Dimensionless means we don't have dimensional. We just use the unit. For example, we use the length divided by diameter. Meter divided by meter, you don't have unit. It's just a ratio between the length, or in this case, LE. Refer to the effective length. E divided by the diameter of your pipe. if the value is 0.006 Reynolds number, means 0.06 times Reynolds number, you get laminar flow. Definition of Reynolds number was given just now. And if you get number 4.4 times 1/6 root of your Reynolds number, then you have a turbulent flow. So these two formula, when you see that the question mentioned laminar flow inside the pipe or turbulent flow inside the pipe, then straight away you pull out either this one or this one. Okay, straight away use this is determined by experiment data already. So straight away you plug in either this one or this one for laminar or turbulent condition. So if the question say in the entrance region you have or inside a pipe you have laminar flow, straight away pull this equation, and this equation again is to determine your length, the effective length to have your laminar flow develop, or the diameter that you must have to get laminar flow. This equation also, right? This E, this L means the length that you should need to get turbulent flow, or the diameter of the pipe that you need to get turbulent flow. Because in engineering, sometimes you need laminar flow, sometimes you need turbulent flow. Depends on the operation that you need. Okay. So these two are also very important equation.
For traditional.
Again, transition is a very complex case to analyze because it's happened very fast. It happened from laminar to turbulent very fast. So usually for this chapter, we do not look at transition flow. We do not look at transition flow because there's no meaning in application. You either use laminar flow or you use turbulent flow, or you either see turbulent flow or laminar flow, because transition is just a flip over process. It's just a very fast process happen. Yeah. Okay.
Like a transit, either laminar or turbulent.
Which one? Oh, your question is transition is whether laminar or turbulent, is it? Is that your question? Transition.
Yes.
Yeah. Transition flow is actually a process to your flow change from laminar into turbulent flow. It's a mixture between laminar and turbulent. You cannot say that it's laminar, or you cannot say that it's a turbulent. It's a mixture of laminar flow and turbulent flow. It's a middle process. Do I answer your question?
Yes, sir.
Okay, good. Now we look at fully developed. Right. We look at fully developed process. Okay, fully developed process. So if you look at the diagram, we have a velocity profile at section 2. And then we have a center line here. We always measure from, if you look at a pipe, we always look at the center line of the pipe, which is where we put our reference axis. Here, x-axis, and then your y-axis or your z-axis, we use r, radius from the center point. Radius from the center point. Radius from the center point. So our velocity, we try to what we're trying to do now is that we try to define our velocity in terms of R and X. We try to develop some mathematics model here. Okay, so so this one is I think it's under question 7. All right, question 7. Question 7 or above question 8 that you see this is the same diagram there. Okay. Now the equation for the a few slides later on, you don't need to copy at this moment. Later on, you can go back to my slide and then you fill in the answer later on, right? So here at this moment, I want you to focus on the slide itself. At least you understand, right, how you develop the equation. Okay, so this is a few methods that we use to derive the equation. First one, we use Newton law, F equal to ma. Then you use a Navier-Stokes equation. Navier-Stokes equation. So it's a very complex equation. However, in this module, I won't test you on the development of Navier-Stokes, but I will test you on the application of Navier-Stokes. All right. So it's a very complex, a very lengthy equation. So we can spend a whole semester just on this Navier-Stokes equation alone, right? If you study mathematics in major, then this one can be one whole chapter, right? But for this module, we only focus on application. So at least you heard Navier-Stokes equation before. And then we will use dimensional analysis method. This is the one that I repeated for the last few example. That for example, we change joule energy to kilogram, meter, and second in that kind of unit. So this is called dimensional analysis method. So again, for today's lecture, I will skip all the equation derivation slides. You can go and read. So you just get some idea how the equation come from. Okay. I'll just look at the slide and try to understand what I'm trying to do. We have a few parameters we need to focus on. Time, t, and then the length of the control volume here. Length, and then radius r, again from the center of the pipe, and horizon. We're going to look at TLRD put in term to develop the velocity profile, this one. We try to define this velocity profile using T, L, R, and D. Which is the equation we try to do in question 12. The equation that you see in your question 12 in your tutorial. So it's a very lengthy process. Okay. What I highlight here is that as a flow through pipe because of the friction, then the velocity is not uniform, just to highlight. Okay. So in the fully developed section, fully developed and steady section, so the flow will flow in the same direction and no acceleration. No acceleration means your flow do not, the velocity do not change from one point to another point. It means acceleration. How you calculate acceleration? You take v2 minus v1 divided by t, right? So in this case, our v1 equal to v2, so we don't have acceleration in the fully developed steady condition. In the diagram above question 8, you see this kind of shape. This shape we call it velocity profile. We call it velocity profile. Okay, so just for your information, again, you'll see some weird symbol. For fully developed, you will see this symbol. This is a mathematics model symbol, and it covers in the Navier-Stokes equation. So just have a look in it. You don't need to memorize this one. Just Just have a look at, oh, you see this one before, means V times D, V dot is a dot product, V dot change of del V equal to U del U del X in X direction. Okay. Wherever you see the inverted triangular later on, inverted triangular, it means del something, huh? Means del in this case, because we look at velocity, so we look at del U over del X in the X direction. Okay, so this is just a mathematics symbol that we will use so that we don't need to always repeat this equation. Okay. Yeah, flow steady, then no acceleration. Streamline, we already cover what is streamline. So yeah, if you have a steady, then means that your streamline is in the same direction. Okay, derivation of equation for the first one, because we have 3 methods to derive the equation just now. F equal to ma, and then we use Navier-Stokes equation, or we use a dimensional analysis. So the first one, I will show you by using the second Newton law, F equal to ma, to derive the velocity profile. So F equal to ma, if you pull out the section, as you see on the screen here, you can convert your pressure times area, you get force. From left hand side, pressure times area, you get pressure on the right hand side, and then you have a shear force. You have a shear force. Shear force, how this shear force come from is from the reaction contact between your water or the float with the wall, huh? So you will get a shear force. Okay, if you don't understand what is shear, you need to go back to your finite element analysis chapter or your static or dynamic chapter when we talk about shear stress and normal stress. So this is shear stress, right? So we convert pressure, we convert shear stress into a force. Then we sum everything equal to 0. Okay, so I don't need to go deep into how you get force already. Pressure times area here. And then this is the change of pressure, because from one point, point 1 to point 2, you have a different pressure. So we have P1 minus delta P. In this case, why minus? Because our flow is from the left to right. Our pressure will drop when our fluid cross a certain length. So there's a negative delta P here, because the energy is lost as the flow from the left to right across a certain distance. In this case is L. Then you have a change of pressure. You convert 1, 2, 3 into a force equal to 0, right? This equation. All right, you take left hand side positive because it's along x-axis, negative because it goes against the direction, and negative again because it goes against. Right. So you can look at shear stress as the friction or resistance, resistant force that exists between the float and the wall, the water and the wall. So there's a resistant force, right? And this force also a resistant force to keep the flow from flowing. Okay, and you sum up everything, then in this equation you see the relationship between R and L. Okay, I'm going to. So you rearrange everything. You arrive at this equation, which is the ratio between pressure and length, and also shear stress and the radius. Right? you rearrange F equal to MA equation, means the force inside the system equal to 0. You rearrange, you get a ratio between pressure and length, and equal to something shear stress divided by R. Okay, this one become this one. So this is we talk about balance in force. Okay. So this is just a mathematical derivation. So we try to put our equation in a certain form. So we know that our shear stress we can put in the certain, we can link our shear stress with our R with the constant value C, this term here. So we want to know the C. How do you find the C? It means every time we want to find a constant value in either derivation or integration, then we'll use boundary condition. The first boundary condition we use is R equal to 0, which is here. Here. We don't have resistance, because here we don't have contact with wall. So R equal to 0, stress equal to 0. However, at R equal to big R here, or D divided by 2, your shear stress become maximum because it's the highest resistance force between the float and the wall. So we can rewrite as shear W, means the wall shear stress. And then we apply the definition of shear stress. Rearrange the equation. You will get these two equations. This one is from F equal to MA. You summarize it. All the force equal to 0 inside the system. This one you derive from shear stress definition. This one. Shear stress equal to constant value R. By boundary condition, you get the second one. You substitute this one inside this equation. You get delta P equal to this term. So when there is no viscosity or no friction, then there's no change of pressure. Delta P is a change of pressure from 0.1 to 0.2. In this equation, if your shear stress equal to 0, the whole equal to 0. So delta P equal to 0, it means that when you have a smooth pipe, there's no change of pressure. Okay, I repeat, if based on this equation, you can prove that when your pipe is super smooth without friction or no viscosity, there's no change of pressure, there's no drop of pressure in the pipe. Delta P equals 0. Okay. All right. So what happened? You have a longer pipe. If you look at this equation, delta P equal to 4L wall shear divided by D. What happened to the pressure? Will it drop or will it increase if you have a higher length here? Vina, are you there? Vina, are you there? Let me check. Do I record? Yes. Okay, who is not here? I only have 7. Hold on.
Beeline not here, sir.
Okay, Bila not here. I will send a message just as a warning. 447, just as a note for this Sue, are you there, Sue? Su Jinghao.
Yes.
Okay, Su Jinghao.
Bila say he have connection problem.
We'll come back to Bila problem later. Now, Sue, you try to answer this question. Based on the equation that I show on the screen, delta P equal to 4L shear W divided by D. What happens if you have a longer pipe to your, what is the effect on the pressure if you have a longer pipe based on this equation?
Longer.
Yeah, you have a longer pipe. Means your L is increasing. What happened to your delta P? This is mathematics. Huh? You understand this equation or not? Do you understand this equation? So you look at this equation, so you look at this equation, delta P equal to 4L shear divided by D. So what happens if your L is increasing to your, what happened to your P if you keep increasing your L? Other keep constant. What happened to your P?
Also increase?
Yes, correct. So it's not increase, it's a change of P, delta P will change.
Okay.
Delta P will change, means the value of delta P will change, right?
Yes.
Okay, then you look at this diagram that I show on the screen. So if your pressure delta P here is keep increasing, what happened to the pressure at section 2? Will it drop or will it increase?
Drop?
Yes, it will drop. So because why? Because our pressure will drop when our L is increasing, because before this already defined that our pressure on the left is higher as our flow is moved forward to the right. So our definition on the section 2 here is P1 minus delta P. So as our delta P increase, more amount will take away from this side. So our pressure will drop.
Okay, so I understand.
Okay. So yeah, what happened if we have a smaller diameter? Praka, are you there? Praka?
Yes.
Yes. Okay. Try to solve this question. What happened if you have a smaller diameter? What happened to your delta P? Smaller diameter. What happened to your delta P? Will it increase or will it decrease?
It will decrease.
Will decrease. So let me rephrase again. So if you have a higher D, so
Okay,
D increase means bigger number. So you divide something with bigger number, what do you get? Okay, 1 divided by 2, 1 divided by 4, 1 divided by 8. What will the number become? Smaller or bigger?
smaller.
Smaller, right? Smaller?
Yes.
Yeah, smaller. So if you have a bigger pipe, means your delta P will become smaller. Delta P will drop if your D increase.
Oh.
Okay, so your if you use a bigger pipe, your delta P will drop, means the pressure drop will be lesser compared to a bigger diameter. Okay, so this is means by this equation. So again, in your coming test, we are looking at your intelligence in solving question. So by looking at the equation, what does it mean? How you modify the question, or how you improve the system. For example, you get a certain value of d, then I ask you to improve the velocity, or get it become to Reynolds number, a certain Reynolds number, make it become a laminar flow or turbulent flow. Then these are the parameter we're looking at, either P, D, or L, or shear stress. So these are parameters we're going to use. So, okay. So again, you can say that these three equation is very important, because we always look at either laminar or turbulent. For this module, we do not look at transitional flow. Okay, at least I give you hints already. I will not ask you on transitional flow. Okay, the next one is just a derivation to question 12. So just a mathematics model. So the definition of shear equal to d mu over du dr. So this is all the definition you can read from the slide. So you just replace what you have there, and then you integrate to get the u magnitude, the velocity in x direction. Okay, so later you can look back at my slide to further digest what is the equation. All right. So this is again, when you integrate, you get a constant value. Strategy we use is to use the boundary condition. What happened in R equal to wall? What happened to in the middle? So at wall, your velocity equal to 0, R equal to d2. So in this equation, u0, R equal to d divided by 2. So your C constant value equal to this value. You substitute back, you get the equation of u, and then you rearrange to get the equation in your tutorial question 12. Okay, so you further reduce this one. This one is in a pressure, mu and L. And then what else? This is what defined for the velocity. In the VC is a center velocity. Here, if you look at the diagram, here, VC, right? So at the end, you will get the equation that you see in question 12. Right. This is just a derivation. So later on, what is more meaningful is this equation, that it link up with our velocity, with our shear, our diameter, our mu, and radius. Okay. So you can look back on my slide on the derivation on this one. Important is this equation. Okay. Then the next one on question 13. All right. So again, just highlight to you that question 12, that equation is very important to define velocity profile. U column R, this means your velocity in the R function, means R change with U change with R is a function. So it means it's the same as fx also. Go to your y function. So this is an equation, right? This is an equation, and we know that our equation equal to y equal to mx. You have a linear equation. You know that if you have a quadratic ax squared plus bx plus c, you will have quadratic equation. However, if you flip these two, your x become constant value, means you have x equal to y square something. It means you will get something in this shape. Okay. So in this direction, in this, you compare the general direction and general equation and this equation. So you can know that you have a quadratic equation here. However, this one was on the y direction or on the r direction. Okay, it's on the r direction. You try to link your mathematics understanding on the graph shape to this structure, the structure of your velocity profile. Okay, so you see here is a quadratic shape. Although it's a parabolic, but if you have a square, means you have a shape like that. Okay. Important is on question 13. We try to develop the Poiseuille law, which is given by Q equal to pi d power 4 delta p 128 mu L. So how do we develop the Q? We know that Q equal to V times A, right? We know that Q equal to velocity times area. So again, this is just a dissect of your cross section. So if you cut your part and put in view from the front, you'll get from the center point to radius R, and you have a you have a small tiny area. How you calculate area in a cylindrical cross section? You take 2 pi R means the perimeter of your circumference of your circle times the dr, you get area, right? The A equal to 2 pi R dr. So this is from, right, to calculate the area for cylindrical. So we know that our Q flow rate equal to VA, Q equal to VA that we see in chapter 2. So this is just a change put in terms of integration, because we want to see what happens if we change the dA. So Q equal to integrate U dA. So why we use U in this direction, in this equation? Because all our flow is in X direction. So you know that again, call your vector form. All the velocity vector to X is U. All the velocity to Y is V. All the velocity to Z is W. Okay, so this is how we look at. So when we develop equation, we need to be careful on the velocity vector. In this case, we use a small u to represent is along x-axis. So pull in all the equation because we want to look into R relationship, because just now we developed the equation, the profile for in terms of R and R. So we pull this term inside this equation, and then you do the integration, find the unknown constant value by the boundary condition. All right, you get this one. All the integration step I will skip very fast. You can study it later on. So at the end, if you integrate with a boundary condition 0 to R, you don't have constant value. Straight away you have a finite value. So at the end, you get your Q equal to pi R square VC divided by 2. Again, the relationship of VC was given in the slide. So VC, right? VC equal to this one. VC equal to this one, centerline velocity. VC equal to this term. Then you rearrange, because we're interested to find what is Q. So we know that Q equal to VA, rearrange become Q divided by A. So, and then you put in the Q in terms of, you put in this one, put in here, you get V equal to VC divided by 2. Put in what is the definition of VC just now. Put in definition of VC, get this one. Then pull back Q equal to VA, right? Then you'll get this equation. So this equation is called Poisson law, Poisson law. For this chapter, Q equal to pi d power 4 delta P divided by 128 mu L is very important when we have a laminar profile, because we are using VC and velocity profile of this one. And of course, you can use this equation for inviscid flow also. Okay. Yeah. So again, this one is called Poisson law. This is in question 13. So how we derive that one, you can look back at the slides. Again, we'll focus on application of equation. So just a note in question 13 there, Poisson law, just a note, it's only valid for laminar flow only. This one. Equation for question 13. Q equal to this one, Q equal to pi d power 4 delta P divided by 128 mu L is only valid for laminar flow. Okay. Okay. And so far we look at horizontal pipe. So what happens if you tilted your pipe at a certain angle, like you see on the 14? So if your pipe, let's say this is your reference axis, if your pipe was in this direction with the angle or theta, this orientation we call it uphill orientation. If your pipe is in this direction, this is theta, or this is positive theta, this is negative theta. This orientation of your pipe is called downhill. Okay. So in question 15, you can see the word uphill and downhill. It means the orientation of the pipe. All right. In question also, sometime we won't give you the diagram. We'll give you a horizontal pipe orientation like that, and then we'll give you a scenario. So what happens if it's uphill and downhill? So again, the derivation of the force that we have here, we use F equal to ma law, means we will equalize all the force inside the system or inside the free body diagram, like what we did to get the Q, to get the delta P and all this. All right, just now we have the important three equations just now. Right, just now we have the first one. This is for question 15, just write it down. I won't go through the derivation of equation already. I straight away jump to what happens if we have a uphill and downhill. Of course, you can go and derive the equation if you have time. All right, I straight away give you the application. So when you have a horizontal pipe, you change to uphill pipe like this diagram with the theta positive. What you need to modify the equation is your delta P, you minus specific gravity, L, length sine theta. Okay. You can prove this equation by equalizing all the force, like what we did for delta P just now. I just don't want to go back to all the derivation. All right. So for question 15, we do some modification on the equation. The first one is the ratio between delta P and L. So if we have an uphill, we use this one. We add a negative gamma L sine theta on the delta P component. If we want to calculate the velocity inside the part, V, just now we have delta P d squared over 32 mu L. So what we do is that we will again add in this component, negative gamma L sine theta, to the equation if we have an upstream. Right? It means that if you look, okay, let's look at one more. If you have a Q, this is a Peirce law again. What you do is that you modify the delta P again, negative gamma L sine theta. So these are the modification to the equation if you have an uphill orientation. And just a side note for this one, it's just that what make this term come into place is that the action of gravity on the mass W itself. If you look at the diagram on the free body diagram here, you look at there's an additional component on your W. This one. There's an additional component because of your fluid weight. All right. And even you do not develop the equation, you think logically, if you try to pump something uphill, your pressure will drop. Right? Something will take away from the delta P. If you pump something from low ground to high ground, your pressure will going to drop because of the elevation. All right. Velocity also will drop. Mass flow rate will also drop because of the gravity force. Okay. Again, the detail of the derivation, you can do it if you have time to do the same process when we talk about delta P divided by L equal to 2 shear stress divided by R in the previous slide. What you need to do is you modify the relationship, all the force equal to 0 here, right, in the x direction. Then at the end, you will still get this relationship. Then you keep in substituting into the later equation. You can see the delta P component will come with a negative gamma L sine theta. Okay, we look at application of this one. Then we go for a short break. Okay. Question 16. Let's look at okay, Bila come back. Bila, you need to review back the video, the part that you missed just now. Okay. Okay. Interesting part. We look at application of knowledge. Question 16. So you have an oil with viscosity mu 0.4 and density rho 900 in the pipe diameter given. We need to find a few things. So the first one, we find the pressure drop, which is delta P. We need to find delta P to create flow rate Q of certain value. If the pipe is horizontal, orientation is horizontal, means we use the equation on the left just now. We use equation, these three equations to solve this question. Everything on the left later on. And we have our length. Our length is 10 meter because we take x2 minus x1, you get 10. It becomes your L. Second case is that when we have a angle, uphill angle, right? We have an uphill angle. what happened to your delta P? What happened to your delta P? And then for scenario in C, if your P1 is 200 kilopascal, find the pressure at maybe in the middle of the pipe. What is the pressure there? Right. So meaning in the uphill pipe, what is the pressure there? Right. How we apply our equation? Right. Again, pull out all the important parameters as usual. So let's solve for the first one. So it asks you to find the delta P. So again, we only have three equations to look at. And we are given a Q. So pull out the Q equation. The equation in question 13, Bristol's law, Q equal to pi d power 4 delta P divided by 128 mu L. Because you want to find the delta P, you rearrange this equation. Put your delta P to, or you pull everything to the left-hand side. You'll get delta P equal to 128 mu L Q divided by pi d4. Because we are given the Q, we want to find P. So look for equation that have the unknown that you want to find. So in this case, we have the Q. Then we rearrange the equation. We get delta P equal to 128 mu L Q divided by pi d power 4. Make sure you use the correct unit inside the equation. Substitute. Just a reminder, in exam, you need to show your steps. Although in the lecture, I do not show you the substitution of number. But in exam, you need to find. So if you substitute the value later on in your own time, the reference answer for you to check is the delta P will be 20.4 kilopascal. Again, just extra notes. What is Pascal? 1 Pascal equal to, Pascal is pressure. Pressure equal to force divided by area. So it's a Newton over meter square. Again, what is force again? F equal to MA. If you need to further do conversion, this is the way you do it. So mass equal to kilogram. A equal to acceleration equal to mass divided by second square. So, and then you put inside this equation. So when you put inside in the Pascal, in Newton, so you will have kilogram meter over meter square, second square. Take out the M, you'll get kilogram over meter dot second square. Okay, 1 Pascal equal to kilogram over meter second square. So this is how you do dimensional analysis. All right. Any question on the first one, on the section A? Any question? No, okay, I'll move. Now, what about B? B means we use the equation on the left-hand side. On the left-hand side, because we have an uphill. So since we have an uphill, we have a steep hill. In this case, because the question do not tell you whether it's uphill or downhill, so we assume it's uphill. So sine theta more than 0, in this case is positive value, sine equal to positive. All right, we use the uphill equation. There's no pressure drop in this case. All right, because yep, no pressure drop. So delta P 0. So you rearrange the equation, you'll get sine theta equal to something. You substitute all the value, you get a constant value on the right hand side. Use your calculator. Sine minus 1 means you do the transpose. You get theta equal to something. Theta equal to negative 13.34. Okay, just go back to the upstream, downstream. Just now I think I missed out something note there. Now, if the flow is downhill, means it's coming down like that. Your sine theta less than 0. If the flow is uphill, your sine theta equal to positive, more than 0. If we go uphill, your sine theta more than 0. If it's downhill, sine theta less than 0. Just let you know in this case. Right? This applies to all the sine term inside there. Right. All right, and the angle we calculate from like this. This is positive in this case. So what happens if we have a negative in this case? It means that what we assume is wrong. It means because we assume is going up and the angle is positive like that, what we get is negative here. It means that our orientation in this case is going down. Means our pipe is going down with the angle 13.34. Important. Important to explain what is negative. Okay. Any question for part B? Any question want to ask me?
No.
Okay, now, right. So number C is that what happened in the center? So we call back just now the equation of sine just now. Because sine equation, this one we don't have the length, but we have the Q. Remember, Q equal to VA. So we can call back all these things. Right. But however, this is just a trick question to ask you. Again, why? Because the pressure is constant along the pipe. So the pressure will be the same. Section C is just a trick question. Usually you will see in the exam. It's just to test your conscious mind, whether you are panic or not panic in the exam. You need to be calm. So in this case, it just tests you whether you understand what is the constant pressure inside. Because the location that they ask you is inside the control volume. Okay, yeah. Yeah, any question? Any question for question 16? So just a summary of this session is that, yeah, this slide is important. So on the left hand side is for the horizontal pipe. on the left hand side is horizontal, on the right hand side is what you see on the screen here on the left hand side diagram, and the theta is positive anti-clockwise direction orientation, and this is called uphill. All right, and sine theta more than 0. So if we have a downhill, means your pipe is going down like that, your theta is like that, so sine theta less than 0, then all these will be you use a negative value there. Okay, so this is just a note for these slides. So again, this slide is very important. Yeah, just to remind yourself that this 6 equation is very important for your coming exam, right? It's more on application, right? And you must tell whether it is either going up or going down. And again, section C, this one is just a trick question because anywhere you measure inside the pipe will be the same. The pressure will be the same. Okay, no matter it's horizontal pipe or it's uphill pipe or downhill pipe, the pressure inside there will be the same. Okay. Again, trick question. This is can say as a trick question or just a bonus mark if you understand what does it trying to ask you. Okay.
Sir. So regardless of the uphill or downhill, the pressure inside the system will be the same, is it?
Yep. Because inside pipe, any point that we look at is the same. All right. Yeah, inside the pipe, everywhere is the same. Inside here, but inside this pipe, because you're looking at a fully developed laminar flow. Okay, because we have a fully developed laminar flow, so every pressure inside this one will be the same. Okay. Okay. 5:30. You need break or you want to straight away go until 6 o'clock? We will stop at straight at 6 o'clock if we don't have stop. What you guys think?
No need to break that, sir. Just continue.
Continue,
Yeah.
Okay, let me check any reaction from the floor. Okay. Nobody object, we will straight go and then we stop at 6 o'clock. Okay. Clear the okay, just a reminder again. You need to know how to explain now when you get a negative. It means what you assume here is wrong. Okay, now the next one is from question 17. Question 17 until question 22, I will skip because it's a dimensional analysis. We will come back if we have time. Okay, so just a note on your tutorial, question 17 until question 22. We will come back when we have time. However, the information will be included in the PowerPoint slide. Right, it's just a derivation of equation, so it's quite a boring chapter, section. So you can go and read. It basically is about nervous stroke equation. Yep. So I'm going to skip all this. You can read. Right, all these equation flying in and out. So you can read. This one, all these you can read. Okay. Okay, we look at question 22, 23. Straight away jump to question 23. Question 23, there's a diagram link at the next page. Just as you can see on the screen here, there's a diagram attached to question 23. So actually, just a recap what we learned this afternoon is that based on Reynolds number, if it's less than 2100 is laminar, it's more than 4000, then it's turbulent. So again, if you plot a graph, as you see from the diagram above question 24, this diagram have 3 axes. On the left is U with its long x-axis inside the tube. Below is time, and on the right hand side is the Reynolds number. And this Reynolds number is used Vd divided by kinematics viscosity. So Vd divided by mu, or right. So important that is you look at the magnitude of the velocity. Is that if you see laminar flow, the U is very constant. The U is very constant, straight line, right? And turbulent flow, the U is keep increasing. It's not stable, right? And you look at the Reynolds number here. If anything that below 2010 is laminar region, anything more than 4000 is turbulent. So again, what happened in the transition? It happened very, very fast, right? So it's very hard to, it's very hard to conduct experiment to observe laminar to turbulent. Okay. This is about laminar flow and turbulent flow. This graph is about U, velocity in x-axis, and Y is your R. So if you can see on the left-hand side diagram, I think this one I do not give it to you because it's just an illustration of what happened in the laminar and turbulent. So in the laminar, you see the velocity in the 0.1 and 0.2 will be different. And then the vector, velocity vector is straight line, rather compared to the turbulent. Turbulent here, there will be a lots of direction changing in turbulent flow. Okay. All right. Next one, we look at question 24, which is part of your module. We're going to look at Cherry equation, CHEZY, Cherry equation, and Darcy equation. Again, we're still at a fully developed turbulent flow, fully developed flow, and this one we look at. So this one I extract from one of the textbook, not same from the reference book that we have. So I extract from the fluid mechanics from this person. Right, I extract from chapter 10 from this book. If you're interested, you can go look for it. It's under Pearson publication. All right. Okay. Now you have the diagram there. Again, this is the derivation steps, so you don't need to copy now, but stay focused on the screen. Later you can copy into your tutorial sheet if you want to. Right. So just understand the way we do it, right? Understand the principle, we do it. So again, we have a green color line here represent pipe, and then with the flow inside, and then we have a downhill orientation. In this case, maybe it's uphill. We assume that the pressure is let's see how it goes. So again, we have a orientation, the angle theta here. And as usual, we have a few parameters look at: pressure, change to force, times area, change to force. We have a shear stress at the wall times the area, L times L times the weighted parameter. P means, okay, you imagine this is a pipe and you have a flow flowing. So we have a cross section there. So what is the rho 0? Rho is a shear. Shear acting parallel to the flow. This is shear times area that the float contact with. This is a float contact area, or in the word called weighted parameter or weighted area. How you find area is that you area length times the perimeter or circumference of the circle. All right, so shear times L times perimeter. This is perimeter. Okay, I try to avoid the use capital P. I use a very special symbol with the highlighted P here. With the highlighted P to represent perimeter, to differentiate between pressure and perimeter. Okay, so it means shear stress times area, you get force also. Force because of the shear. Okay, derivation. Assumption, uniform steady momentum equation. So pressure times area force, and the left hand side section 1 equal, because it's going up, because this is X, this is R. So its opposite means negative. Negative means it go against the axis. LP times W psi, because we have the mass from the water. So derivation of this one, you look back at the diagram before this, meaning we have a force going east, then we expand the W into R direction and X direction, right? And W equal to rho G times the velocity. All right, this is mass, your weight, right? Psi relationship, if you look at this diagram, so our point here, so what going down is negative, that's why we have a negative delta Z in the equation, because it's going down, divided by L is here. So psi equal to opposite divided by hypotenuse. So that's why we have negative delta Z divided by L. Substitute the value inside there. All right. You'll get this equation. Right. So this one you can read from slide later on. Yeah. This is just a side note. If you take A divided by the perimeter, is known as hydraulic mean depth. All right. If you take A divided by the weighted parameter, this one, not pressure, area divided by weighted parameter is known as hydraulic mean depth. We will replace hydraulic mean depth as M. Okay. The rest is mathematic arrangement. So when we want to put, this is another definition for shear stress, right? So shear stress equal to your hydraulic mean depth times the change of pressure along x-axis. Okay. I will not go back to detailed definition, detailed derivation, just straight away pull out what is this one. All right. And then there's another definition for shear stress also, but in terms of mean flow velocity. So definition 1, this one. Definition 2, this one. So equal these two, you'll get this one equal to what, right? So this term is in the average velocity. This one is in the our M is our hydraulic mean depth, A divided by P. So we link up with our another definition for our loss, friction head loss, HF, FL V square divided by 2GM. Again, this one is the third equation, a new equation that you learn on these slides. You substitute in, you get the P star divided by the X. This is the change of pressure along X in the different term, mathematical term here. All right. So you can write this equation in this term. Right. dP dx equal to dx P times rho jack. I need to mention that the Chesney equation in question 24, the word Chesney equation actually is derived from the open channel. But I don't know why they purposely put the open channel and the tube and a pipe system together. All right. So this is just a derivation. dz over dx is sine theta. You can see from here. Z over x. The x direction is here. So dz over x is your sine theta. This is again just an if you look at a note here is for open system, open channel system. And we assume it's a uniform flow. We can do some simplification assumption. HF divided by L hat equal to sine, then we put an I there. Then we sum everything, recall what we've done so far, substitute inside there. We get one equation. So what is important is that you get this one. All right. So Chesney equation is about velocity, average velocity. Just remind yourself, when you need to use average velocity, sometimes you need to call back or you learn about Chesney formula given you by V hat equal to C square root of I. So MI, okay. Again, M is given in this slide. Right. For pipe, there's for pipes, pipe system with the full of float, then the welded parameter become internal circumference of the pipe, which means our M defined by A divided by P. So A equal to D pi D square divided by 4 pi D. Then we simplify, become D divided by 4. And this is just a recall some information that we can use the Chesney formula. Every time you see average velocity, because in turbulent flow, we will assume in turbulent flow, we will always use average velocity. Laminar flow, we don't need to use average velocity. But for turbulent flow, yes, we need to use Chesney equation so that we can continue to solve problems using the average velocity component. And the Darcy-Weisbach equation is this one. All right, it's just FL V square over 2GM equal to HF equal to so forth. Right? So just a make note that in your revision notes, this slide is important. It summarizes what you should know, what is Chesney formula, and what is Darcy-Weisbach equation. Right. Derivation of Chesney formula, you can read my slides later on. Important for today is that you've seen before what is Chesney formula. Is V hat equal to C. C is a constant value. So C is this one, square root of 2G divided by F. Square root of MI. M is A divided by P. Yeah, and then you substitute. Okay, so again, just to summarize what we learned for today. Chesney equation is very important. Then we look at this one. You go to question 26 because I jumped a little bit. Question 26. You look at the head loss. We have two types of head loss. We have two types of head loss. We have this is question 26. Question 26. You deal with two types of head loss here. So we have major loss and minor loss. Major loss and minor loss. So HL major and HL minor. What is the difference between these two is that major loss normally is deal with viscous effect. Viscous effects. In the straight pipe, the keyword is viscous and straight. Viscous effect and straight pipe. While for the minor loss is about component. For example, palm, T-bow, T-elbow, elbow, and all this. Then it becomes minor loss. Major loss is more on the viscous effect, we deal with shear. This one. Or mu, dynamic viscosity. Or this one, dynamic viscosity, and yeah. Total head loss equal to combination of these two. So there's an equation to combine these two. So this is question 28. Question 28 asks you what is delta P and HL head loss? They are dependent on what? So they are dependent on the shear stress. Okay. This is just a fundamental understanding. What happens if you see some parameter given in the question? If you see wall stress given, then be prepared that you need to find delta P and also to find head loss. And fundamental differences between laminar and turbulent flow. This is question 29. Straight away give you the answer. So turbulent flow link up with However, laminar is on the viscosity. Laminar doesn't care about density. When you have a laminar flow, it doesn't care about density. However, you look at viscosity. For turbulent flow, what can determine whether it's turbulent flow is the density of the flow. Okay. So this is the answer for question 29. He asks you to differentiate what is laminar and turbulent flow. Rather than this is another definition or another observation of turbulent and laminar flow. So earlier we looked at Reynolds number. As it certain number, we get laminar flow and or turbulent flow. And then this one is just a general mathematic form that we look at when you change density, then something will happen to the turbulent flow, right? Right. So this is about when you focus on major loss, HL major. This statement is for HL major that link up with shear stress. These two statements is only apply to major head loss, HL major. And just now the slide tell you what is major loss is due to viscous effect. All right. Question 30 I will skip because it's a derivation of equation. It's just a dimensionless analysis. When we have time, we'll come back to question 31. Yeah, this is just again some illustration on the viscosity, how it can affect your major loss HL. So what does it mean? It's just that turbulent flow. I think this one is the question 31. So turbulent flow, there is a thin viscous sublayer formed in the fluid near the pipe flow. It is here. This is turbulent flow, right? So when you have turbulent flow, if you zoom in the surface here, you'll see there's a change of streamline because of the rough wall, right? Because of the rough wall, right? And this explained in this phrase, right? So in turbulent flow, your delta P will be looked at wall roughness. It is F. And if you can compare to laminar flow on the right hand diagram here, you don't have any viscous effect. So for laminar flow, there's no thin viscous layer. Viscous effect are important across the entire pipe. Sorry, this just now I mentioned is F. No, it's not F. It's this sign. This is wall roughness. Wall roughness. So, okay, so this is 31 and 32. Okay, again, this one is for question 30, not mistaken, on the derivation. You will just read through this slide. The loss of equation, I don't want to confuse you. And what else? This one. Question 33. Okay, question 33. I want you to write this equation under question 33. This one is called mechanical and energy equation that we see, I think, before we break. Right. Again, this one with no shuffle. We take out the shuffle already. Okay. So now you see all these terms in the equation. Just now we don't have alpha, alpha 1, alpha 2. Right. So just as you see on the slide here, you'll see that alpha 1, alpha 2 will have equal magnitude when you have a fully developed flow. Right. And the rest will be the same. So you have, when you have a constant d, your velocity will be the same. No elevation on pipe means horizontal pipe. All right. Then Z you can cancel. Fully developed, these two terms is the same. Rearrange, the change of pressure will be gamma HL. Right? And recall what is the equation. All right. So this is the answer for question 34. HL equal to F is the friction. HL equal to F friction L over D times V squared over 2G. This is called Darcy-Weisbach equation. And when does it apply to? It will apply to any fully developed, steady, incompressible. Again, incompressible deal with your delta, with your density. And it doesn't care whether the pipe is horizontal, uphill, or downhill. So it's a general equation that you can use to calculate the head loss inside the pipe. Means head loss is the height of water that it can go. You can say HL is like the height of water that it can go, or the height of a pump that it can go up, and so on. Right? It's a loss. It's a loss of energy. Right? So this is the form shape of a Darcy-Weisbach DW equation that we use to solve question. Right? We'll solve question. Okay. Okay. Just a side note here. So when you have a horizontal pipe, then you can only use this equation. All right. For horizontal pipe, your delta P will be equal to F friction L divided by D times the half rho V squared. Okay. First table that we'll see in exam is that table 8.1. How to read this table is that on the left hand side, you will have a type of material. For example, you're given cast iron. Then your roughness, you read from this table. For example, in question, you have a horizontal cast iron. Then straight away, you use 0.26 value for roughness, equivalent roughness. All right, fixed already. This one fixed already. All the value is only this table help you to straight away substitute the non-value in the equation later on. This one you will need to read carefully the question. So different material of pipe give you different roughness, especially catch question when you have a glass pipe or live tube, your roughness is 0. So this. And the famous chart that you will see for this module, we call it Moody chart. which is on your page 13, which is above question 36. So this is a chart that we will use to solve chapter 3 question and even some of the question in later on. But this Moodle chart, it will cover in your test 1. It will cover in your test 1. So make friends with this chart. Yeah. Okay. Okay. So yeah, this is a name we use for this chart. You look at the axis, there are 3 axes here. One on the left, friction. F is the friction factor. Reynolds number, you can calculate from the question. On the right hand side is the roughness divided by D. So this is where you calculate. So for example, the value of the roughness, this one, you read from the table just now, this one. So you have, for example, you are given a drawing tube, then you get 0.0015 in mm. Again, for this module, we'll use unit SI. Don't read the wrong column. All right. On the left is on a feet. On the right is unit SI. Don't read wrong. Again, don't read wrong. We will use this side, right hand side, because we are using SI for this module. So for example, you want to calculate value for this axis. You want to calculate what is the value of D. You refer to table. Let's say we are having a drawing tube 0.0015. And then you are given the D for your tube. You just put lah. So for example, 0.2 meter. Then you get one value. You read from this chart. Okay. So it's very useful to use this chart. So again, you need to be careful. Inside, what is the content? So on the left hand side, you will see already labeled for you. You have a laminar flow. So meaning vertical line here, all this vertical line represents some of the Reynolds number. So if your Reynolds number is less than 4,000, less than 2,100, it falls under laminar flow, where they follow this line, right? And then you have a transition range, which is very, very small. That why there's no value here, because it's very hard to get data in the transition range. All right, so they might just give you a hint. There might be a trick question to ask you on the transition range. Means if the value fall within here, it means it's a transition flow. And then if your value here, you see this dashed line, whatever value that above this line, it will have a turbulent flow, wholly turbulent flow. Any section, right? And then there's a smooth line here. So smooth means when you have a glass, then you use this line. You follow this line. You follow this line. So you need to be comfortable to read the scale of the Reynolds number. Okay, so this is 10 power 3, means 1,000. And then this is 10 power 4. How do we read? Is that you see 0 means 1, 1,000, 2,000, 4,000, 6,000, 8,000, 10,000 here. This line is 10 power negative 3, but you simplify become 10 power 4. And then follow. This is 2 10 power 4, 4 10 power 4, 6 10 power 4, 8 10 power 4. This is 10 10 power 4 or 10 power 5. Don't read the wrong line. So you have to know that between these two, what does it mean? It means that half of the value. So for example, this one, 1,000 and 2,000, there's a line in between. This is 1.5 10 power 3. This position. And then same with this one. And then this one. 2, 4. There's 1, 2, 3. So you need to call back your graph scale to identify what is the value between individual line. This one. Okay, 8 and 10 also have one line. This is represent 9. This is 7. This one, 4 and 6 got 2 lines, so you need to divide very carefully. All right. So 3 and 4, 2 and 4 also have 1, 2, 3 line. So you need to divide, and each line represents some numbers. Okay. Important on this one because most of the mistake done in the exam is because wrongly read your Reynolds number axis. Put a note somewhere in your notes. Be careful when you read the axis here. On the left or on the right, this one no problem. This one normally is a calculator problem. You press the wrong number or you use the wrong unit, then you get the wrong line. Reynolds number, this one usually you read the wrong. You in the exam you panic already. You read the wrong line and then you get the wrong value. Okay, on how to use we will continue on next Tuesday. All right. Unfortunately, we cannot finish this chapter by today. We will continue chapter 3 in coming Tuesday. Right. Today we end our lecture at Moodle chart here. Okay. All right. Any question so far? Any question?
Oh,
Okay. Yep. It's a very long day. Yep. Let me stop the recording first.